Alright, so I've already gotten a couple questions about these piecewise functions, and I imagine more will come up over the weekend, so I've gone ahead and set up a different example from the one we did in lecture video and what we talked about at the start of class, so that you can see how to do this type of problem. It's kind of the same as what you've seen before, but hopefully now that you've encountered it a few different times, you know the places where you have questions about how to do this type of thing. So I set up a problem kind of like your web work, but not exactly. Here's the differential equation. Here's my piecewise function that splits at x equals 3. If you wanted to, you could draw something that does that. And here's my initial condition. And I'm going to assume that at this point, we've learned enough about this type of problem that we can get here, where we've created our integrating factor and we've gone ahead and actually set up the integrals. And I think you all are pretty comfortable here too, where before the switch point, you just set it up like a normal equation and you integrate your function accordingly. So what I'm going to do now is think about the second part. So on your own or reflecting on prior videos, you should be able to do the case where we say, oh, we break it in half, and I think about the part before the function breaks, between 0 and 3. I get this solution using my initial condition and all that. And this is that second half. Where I'm looking at after the switch. So my left side stays the same. I'm still trying to integrate with respect to e to the 3xy. And my right side, e to the 3xf, is what's going to change. So my function f for x bigger than 3 spent some time at 0 until I hit 3 in x. And then after that, it spent time as sine of x e to the minus 3x. So after I pass 3 up to any random x value I want to reach, my f value is sine of x e to the minus 3x dx. Okay, so what you'll notice is over here on the right side, I've got these definite integrals. The way you did the first half of the problem, you may have picked definite or indefinite integrals, but once you start breaking it up, it's natural to have these bounds here. So to be consistent, I'm going to do it with definite integrals over here. I'm going from 0 up to some random x, except my variable that I'm thinking about isn't actually integrating with respect to x, it's integrating with respect to e to the 3xy. So I really care that I started when x was 0 and y was 1, and I go up to some random x and y. Integrating that just gives you whatever's inside the integrand, evaluated over these definite bounds. And then integrating 0 from 0 to 3 just gives me 0. Integrating 0 over a definite interval gives you 0. And then integrating e to the 3x sine x, e to the minus 3x, those e's cancel out, so I'm just integrating sine. So the integral of sine x is minus cosine x, and that's evaluated from x equals 3 to x being x. So then I end up with e to the 3xy minus, evaluating at my lower bound, e to the 0 times 1, because y is 1, equal to 0 minus cosine x plus cosine 3. And then I could go ahead and solve for y. Y is e to the minus 3x all times e to the 0 times 1 is 1. Move that 1 over to the other side. 1 minus cosine x plus cosine 3. That's my solution. Something that's going to feel more natural to a lot of you is not doing it with definite integrals, and that's okay too. So let's go ahead and try it that way instead. So instead I've got my definite integrals over here. I know that I have to break it from 0 to 3. No, I have to take it from 3 to x. So I could go ahead and do that exactly the same way. This gives me 0 minus cosine x evaluated from 3 to x. But then over on this side, I'm not really thinking about what's happening. I just say, okay, I integrate this. I know I get e to the 3xy. If I go ahead and solve for y from here, what's going to happen is I'm missing an extra term that showed up in my other solution. That extra term is missing because this is an indefinite integral. And if I take an indefinite integral, I need to have plus a constant. When you had like people grading your exams taking off points for missing plus a constant, it wasn't to be a stickler, it was because this constant's really important. And when you do this like first half of the problem, you might not write that plus a constant. Maybe it doesn't bother you, because if you add plus a constant on either side of the equation, you'll be fine skipping one because you have a constant somewhere. But technically, every time you take this type of integral, there should be a spare constant. A lot of the time, you'll just have constants on both sides, and forgetting this one doesn't really hurt you. But if you do it this way, it hurts you to forget it. So, proceeding from here, I would go ahead and say, okay, so y must be e to the minus 3x times some constant minus cosine x plus cosine 3. And there's going to be a temptation when you get to this point to say, oops, let me erase this, that's a little bit more room. To say, okay, I know how to solve for unknown constants. I come back up here, y of 0 equals 1. So I say, okay, I should have 1 equal e to the 0 times minus c minus cosine 0 plus cosine 3. And that's going to give you c equal to like 1 minus cosine 0, sorry, 1 plus cosine 0 minus cosine 3. I'm blocking that. Just when you solve for the c, the thing I want you to recognize is it's definitely not going to be 1. There's a cosine 3 hanging out in there, so it does something besides 1. The reason is because once you're looking at this x greater than 3, the, quote, initial condition that you plug in isn't this one anymore. This function you're solving for starts here. So the initial condition you need to think about is where your first solution ended. This new one better pick up. So instead, what I'm going to need is I say, okay, this other one ended at y of 3 gave me e to the minus 9 when everything changed. And then over here, I'm going to have to think, okay, when x is 3, I should get e to the minus 9 over here, e to the minus 9, negative constant minus cosine of 3 plus cosine of 3. And then these cosine 3's cancel out with each other. My c is end up being like negative 1. Which gives me the same answer I had below. I'm not going to make you watch me do that algebra, but these e's cancel out. 1 equals minus c, c is minus 1. And then that becomes y equal e to the minus 3x times 1 minus cosine x plus cosine 3. Same answer we found the other way. So either approach is fine. You just have to make sure, if you do it this way, don't forget your constant. And then when you're solving for that constant, don't forget that this is your initial condition. You care about when this function starts, not when the entire thing started. You already used this initial condition in the first half, it's gone to you. You need to find new information to see this new curve. If you do it the definite integrals way, all your integrals are anchored from 0, so it actually doesn't matter. And it kind of creates the same constant because it accounts for everything that happened from the very start on both sides. So hopefully this helps clear up how to do that type of problem.